This chapter is about one of the most important functional group families in organic chemistry: aldehydes, ketones, and carboxylic acids. The real task here is not to memorize names in isolation, but to understand how structure, naming, and reactions connect. Once that connection is clear, the whole chapter becomes much easier to handle. Everything in this chapter starts with the carbonyl group. Carbonyl is the structural backbone of a huge part of organic chemistry, and the key feature is the CO bond. That bond is not just a double bond. It contains one sigma bond and one pi bond, and it is strongly polarized because oxygen pulls electron density toward itself. That polarity is what drives most of the chemistry that follows. If you miss that, the reactions will feel random. The easiest way to classify carbonyl compounds is to look at what is attached to the carbonyl carbon. If it has hydrogen, it is an aldehyde. If it has carbon groups on both sides, it is a ketone. If it has OH, it is a carboxylic acid. If it has NH2, it is an amide. If it has a halogen, it is an acyl halide. That one family tree is enough to orient yourself before you move into naming or reactions. Here's a trap you need to be aware of. The neighbors of the carbonyl carbon decide the class, not the carbonyl itself. Carbonyl compounds are not abstract classroom molecules. They show up in fragrance, flavor, and industry. Vanillin gives fragrance, cinnamaldehyde gives flavor, and acetone is a major industrial solvent. That is why this chapter matters beyond the textbook. It connects directly to what you smell, taste, and use in laboratories and industries every day. Nomenclature is where students either become comfortable or get confused early. There are two naming systems here: common names and IUPAC names. Common names often come from historical sources or the carboxylic acids from which they are derived. IUPAC names, on the other hand, follow a formal rule system based on the parent alkane chain. Aldehydes use the suffix -al. Ketones use 1, and numbering is done systematically. Keep that distinction clean because both systems are still used in exams. Common names often use Greek letters to show where a substituent is located. The carbon directly attached to the carbonyl group is the alpha carbon. The next one is the beta carbon, then gamma, and so on. Here's a trap you need to be aware of. The carbonyl carbon itself is never alpha. Alpha always means the carbon next to the carbonyl group, not the carbonyl carbon. That small distinction is tested more often than students expect. Aldehydes get special treatment in naming because the aldehyde carbon is always carbon 1. That is, the VIP carbon. First, find the longest chain containing the CHO group. Then, replace the parent alkane ending E with AL. Finally, number the chain starting from the aldehyde carbon. The example shown here turns pentane into pentanal with the common name Whaler aldehyde. So, if the CHO group is present, the numbering starts from that end automatically. Ketones are named by first finding the longest chain containing the carbonyl group, then replacing the E ending with 1. Unlike aldehydes, ketones are numbered from the end closest to the carbonyl carbon because the position of the carbonyl must get the lowest possible number. The example given is pentane 2,1, also called methyl N-propyl ketone. Here's a trap you need to be aware of. Always minimize the locant. The carbonyl group wants the lowest number possible. Cyclic aldehydes follow a slightly different naming rule. When the CHO group is attached directly to a ring, the ring carbon is treated as carbon 1 and the suffix carbaldehyde is added. That is why a structure like methyl cyclohexane attached to CHO becomes 3-methyl cyclohexane carbaldehyde. For benzene rings, benzene carbaldehyde is the systematic form, though the common name benzaldehyde is still widely accepted. That acceptance matters because common derivatives appear frequently in questions. Some carbonyl compounds appear so often that both their common and IUPAC names become important. Formaldehyde is methanol, acetone is propanone, and acetophenone is 1-phenylethan-1,1. Acrolein becomes prop-2-enol, and mesetyl oxide has its own IUPAC form as 4-methyl-pent-3N-1. This is one of those areas where examiners expect you to recognize both naming styles, not just one. Now the summary ties everything together neatly. Aldehydes are numbered from carbon 1 and use Al. Ketones use the 1 suffix and get the lowest possible locant. Common names often use Greek letter notation like alpha, beta, and gamma. IUPAC naming stays numeric with 1, 2, 3, and so on. If you remember just this flow, you can handle most naming questions without confusion.